product of two subgroup. Here definition: let H and K be two subgroup of G. Define Hk equals to small h k such that H belongs to H and K belongs to K. Then Hk is non-empty, which is subset of G. This is the product of subgroup. Now Hk is a subgroup of G if and only if Hk equals to Kh. इसका प्रूफ करेंगे हम. Let Hk be the subgroup of G. This is the notation of subgroup. Then we shall show Hk equals to Kh. That is, first we show Hk is a subset of Kh. Then we show Kh be the subset of Hk. Let X belongs to Hk. It implies X inverse belongs to Hk, since Hk be the subgroup of G. So we can write now X equals to X inverse का whole inverse is equal to H inverse, that is K inverse H inverse. But this is belongs to Kh because K inverse is the element of K and H inverse is the element of H. It implies Hk be the subset of Kh, number 1. Now let Y belongs to Kh. Now we have to show Y belongs to Hk. Let Y equals to Kh for some K belongs to K and H belongs to H. Similarly यहाँ पे भी वही है, for some H belongs to H and K belongs to capital K. So Y inverse can be written as Kh का whole inverse. This can be written as H inverse K inverse. It implies this must belongs to Hk because H inverse is the element of H and K inverse is the element of K. So Y inverse belongs to Hk. It implies Y belongs to Hk. Why? Because Hk be the subgroup of G. तो Y हमने Kh कर लिया था. Now Y belongs to Hk. Thus we can write Kh is the subset of Hk by 1 and 2. Hk equals to Kh. First part is proved. Now conversely, let H and K be the subgroup of G and Hk equals to Kh. Now we to show what? We to show Hk be the subgroup of G. Hk be the subgroup of G. ये हमें शो करना है. तो हम यहाँ पे वन स्टेप टेस्ट का यूज करेंगे. सो लेट x, y बिलोंग्स टू hk. तो hk में कैसे एलिमेंट होंगे? h1 k1 एंड h2 k2 टाइप के, वेयर h1 h2 बिलोंग्स टू h and k1 k2 belongs to k. X into y inverse can be written as h1 k1 into h2 k2 whole inverse. We can write this h1 k1, this is k2 inverse h2 inverse by reversal law. h1 k1 k2 inverse h2 inverse by associative by reversal. Now this k1 into k2 inverse, k3 h2 inverse, because k1 and k2 inverse is the element of k and k is the subgroup of Z. So we can write this h1 k3 h2 inverse. Since k3 h2 inverse belongs to kh, because this is element of k and this is element of h equals to hk, we may write k3 inverse this element may be written as some element, suppose h4 and k4, fourth sum h4 k4. It implies y inverse, it implies xy inverse equals to h1. So we can replace the value this k4 by associative h1 h4 k4, this is h5 k4, this belongs to hk, thus xy inverse belongs to hk. This is by associative. Therefore, by one step subgroup test, hk be the subgroup of G. We have another theorem. If h and k be the subgroup of G, where G is finite, then order of hk equals to order of k upon h intersection k. This is the most important theorem in this section, where h into k is the product of subgroup. We already defined the proof. Since h and k be the subgroup of G, it implies h intersection k must be subgroup of G, because h intersection k be the subset of k and h intersection k be the subset of h, it implies h intersection k is subgroup of k and h intersection k with the subgroup of also h. Let h intersection k equals to say D. for our simplicity, since D is the subgroup of K, because we know, let K1D, K2D and so on, KTD are distinct left cosets of D in K, because we assume K has T elements. So we can write K equals to K1D, K2D union and so on, KTD, because KID, cardinality of KID equals to D. So we can write because this is also distinct, so we can write, we direct जैसे हमने लैग्रांज में किया था. सेम वही हमने किया है, बिकॉज these all are distinct coset, so we add this cardinality. It implies that T equals to order of K upon order of D, number 1. So again we define HK, we already have HK, so HK can be written as H, where K, what is K? Just define this asterisk, this is union of I equals to 1 to T KID by asterisk. So we can write U of I equals to 1 to T KIHD. Now since we also know D is the subset of H, it implies HD equals to H. So HK equals to I equals to 1 to T KI, HD means H. This can be written as K1H union K2H union and so on, union KTH. These cosets are distinct, then we can write this type. Now if KIH equals to KJH for all, it implies KI KJ inverse belongs to H by property. Now since KI KJ inverse belongs to K, since these are element of K, it can be written as KI KJ inverse belongs to H intersection K, which is belongs to D. If this belongs to D, then we can write KID equals to KJD, but we choose this coset are distinct for distinct I and J. Therefore K1H, K2H and so on, KTH are distinct left cosets. So we can write cardinality of HK equals to K1H plus K2H and so on, cardinality of KTH. Since KIH equals to H, so this is T H HK. So T equals to the cardinality of HK upon cardinality of H. This is equation second. So from 1 and 2, K D equals to HK upon this H. So HK equals to H into K upon cardinality of D. That is, cardinality of HK equals to HK upon H intersection K. Now we have a question. G be a non-abelian group of order 10, then we to show number of elements of order 2 is 5. By Lagrange theorem, the possible order of element in G is 1, 2, 5 and 10. They all are divisor of 10. Since G is non-abelian, it implies G is non-cyclic, because every cyclic imply because every cyclic group imply abelian, so not abelian imply not cyclic. यहाँ से हम क्या लिख सकते हैं? G has no element of order 10. Again, G is non-abelian. Then we cannot say every element are self-inverse. That is, because we know if every element are self-inverse in group, then this is abelian. It implies there exists at least one element of order 5, because all element cannot be order 2. If all element are order 2 except identity, then it become abelian, but this is non-abelian. So at least one element order 5. Say A belongs to G. Order of A equals to 5. Then a set generated by A, suppose this is H, is subgroup of G, but H is the cyclic subgroup of G. Rather, H is cyclic subgroup. Let B equals to K is another cyclic subgroup of order 5. So if these are distinct, then H intersection K must have only identity element. So by this theorem, cardinality of HK equals to K H intersection K, that is 5 into 5 upon 1, but this is 25. This cannot be greater than 10. Thus G has only one subgroup of order 5. it imply, say H. H has 4 elements of order 5 and 1 element of order 1. This is written since this H is a cyclic group of order 5, number of element equals to phi d, where d is the divisor of 5. So therefore phi d equals to 4. So we write this thus: G has 4 element of order 5 and 1 element of order 1. Since order of G equals to 10, possible order of elements are 1, 5 and 2. Here we claim that G has exactly 4 element order 5, 1 element order 4 element of order 5, 1 element of order 1, then rest elements are of order 2. Thus number of elements of order 2 in G equals to 5. Now generalizing this concept for the non-abelian group of order 2p, where p is prime, then G has p elements of order 2. Let H and K be the subgroup of G. If order of H equals to 12 and order of K equals to 35, what is the cardinality of H intersection K? Since order of H, it's odd, H equals to 1 into 2 square into 3, we can write here K equals to 35, that is 1 into 5 into 7. The possible order of element in H equals to 1, 4 and combination of this product and combination of this product, but there are no common order. Therefore H intersection K must have 1 element, which is identity. Next, next questions. If G is a abelian having order odd and belongs to, this is odd, so product of all element, say if G equals to a1, a2, so on, a to n plus 1, then product of a1, a2 and so on, a to n plus 1 equals to identity, because G contain every element and also their inverse. So this is abelian, so it commute and give identity. If order of G equals to p prime, then there is no proper subgroup of Z which is non-trivial. This is simple by Lagrange theorem. This divisor, possible divisor is 1 and P, so it must have either subgroup of order 1 and subgroup of order P. If P, then this is improper, and 1, this is trivial. It has no proper let order of Z equals to say 15. Let order of Z equals to 15 if G has only one subgroup of order 3 and only one of order 5. It has one subgroup of order 3, say H, and only one subgroup of order 5, say K. Then we to show then G is cyclic. Let order of H equals to 3 and order of K equals to 5. Since H and K are distinct because it has element of order 3 and it has element of order 5 and also contain in identity in both, so H union K, cardinality of H union K can be written as cardinality of H plus cardinality of K minus cardinality of H intersection K. This is 3 plus 5 minus 1, which is 7, less than 15. There is X belongs to G such that X doesn't belongs to H union K. By Lagrange, order of X must divide order of G, but X cannot belong to H union K, it implies. So order of X cannot be 3 and order of X also cannot be 5, and also X cannot be 1. Thus order of X must be 15. Therefore G can be generated by this X. It implies G is cyclic. We just proved if group of order is 15, then G is cyclic. Now generalizing this concept, if order of G equals to P and Q, where P and Q are prime, and order of H equals to P and order of K equals to Q, say these are two subgroup of G, then H union K, this is always less than P and Q, P into Q. So there exists X belongs to G such that X doesn't belongs to H union K. By Lagrange theorem, order of X should divide order of Z but here cannot equals to P cannot equals to and Q, or also this cannot be 1. Thus order of X must be P into Q. Now one more question. If order of G equals to 25, then either G is cyclic or G to the power 5 equals to identity for all G belongs to G. Since order of G equals to 25, that is 5 square, possible order of elements A in G is 1, 5 and 25, because order of A element should divide order of group. So if order of A equals to 25, then G is cyclic, done. If order of A does not, if order of A not equal to 25, then G is non-cyclic. Thus G must have one element of order 1, since identity is unique. One element of order 1 and rest are order of 5, because 5 divide 25 for all, because identity is also satisfy this relation. Now this is done.